Hello everyone and welcome to the Control Engineering and Control Theory tutorials. In this Control Engineering tutorial, we will explain the effect of zeros of transfer functions on the dynamical behavior of systems. This important topic is often overlooked or not properly explained in the Control Engineering courses. The general impression that we have is that students often do not understand zeros of transfer functions and their effects on the dynamical system behavior and response. Zeros play a very important role in control system analysis and design. If their effect is not properly understood, one will never be able to design a high-performance control system. Here is a brief outline of what you will learn in this video tutorial. Later on, we will mathematically explain the phenomena that you can see over here. You can see two graphs that illustrate the effect of zeros on the dynamical system response. These graphs show the step responses of two systems. Here's the first system and its transfer function, and here's the second system and its transfer function. On the left side, we can see a minimum phase system with a zero in the left half of the complex plane. The transfer function is given over here. Zeta is the damping ratio, omega n is the natural undamped frequency, and k is the parameter that we will vary in order to illustrate the effect of zeros. This is a parametric transfer function in the so-called prototype form. The zero of this system is a zero of the expression in the numerator. The zero is given over here. Obviously, the zero is on the real axis. By varying this parameter k, we can move the zero on the real axis left or right. By increasing k, we move zero further left in the complex plane, and by decreasing k, we move the zero closer to the imaginary axis. Over here, you can see the effect of the zero on the step response of the system. As k is decreased, that is, as the zero approaches the imaginary axis, the rise time increases. However, the overshoot increases. We will learn that, in some sense, the zero closer to the imaginary axis and closer to the real parts of the system poles plays the role of derivative. That is, it introduces an additional derivative action in the step response. On the right side, you can see the case when the zero is in the right half of the complex plane. This system belongs to the class of the so-called non-minimum phase systems. The transfer function is very similar to the first case with a difference, and this is a very big difference in this sign. That is, over here we have a minus, and over here we have a plus sign. The zero of this system is given over here, and it is in the right half of the complex plane. This fact has a tremendous effect on the system response. Here is the step response of the system. The blue line represents the system's step response. The zero in the right half of the complex plane will create this undershoot, which can lead to disastrous effects in practice. That was a brief outline and summary. But before I start with explanations, I would like to mention the following. It took me a significant amount of time, energy, and planning to create this completely free video tutorial, as well as more than 350 free video tutorials that you can find on my YouTube channel. And consequently, I kindly ask you to press the like and subscribe buttons. Also, if you have some questions or a comment about the material presented in this lecture, please feel free to ask your question or give a comment in the comment section below. Thanks a lot. Okay, let's start. Our first goal is to show that zero close to the real pole attenuates the effect of that pole on the system response. Let us consider this example. This is the second order transfer function with the poles located at s is equal to -1 and s is equal to -4. We don't have a zero over here. Next, let us compute the impulse response of this system. That is, we need to compute the inverse Laplace transform of this transfer function. To do that, we need to use the partial fraction expansion. The partial fraction expansion of this equation is given over here. where C1 and C2 are the constants that we need to find. By using the cover-up method, we obtain that C1 is given by 4 over 3 and C2 is given by minus 4 over 3. For those of you who are not familiar with the cover-up method, I created a separate tutorial that explains how to compute the partial fraction expansions and inverse Laplace transforms by using this method. A link to this tutorial is given in the description below this video. For completeness of this video tutorial, over here I will briefly explain how to compute C1 by using the cover-up method. First of all, we need to identify the poles of the system. The poles are at s is equal to minus 1 and s is equal to minus 4. The next step is to expand our transfer function. Here's the expansion. And let's compute C1. C1 is equal to the transfer function multiplied by this term in the denominator, and we evaluate the expression at s is equal to minus 1. That is, we evaluate the expression at our pole. Consequently, C1 is equal to 4 over s plus 1 multiplying s plus 4 multiplying s plus 1, and we need to evaluate this expression at s is equal to minus 1. C1 is equal to, we can cancel this term and this term, and we obtain 4 over s plus 4, and this should be evaluated at s is equal to minus 1. And as the result, we obtain 4 over 3. And here's the result. By using the same strategy, we can compute C2. And consequently, we can expand our transfer function given over here like this. The impulse response in the time domain is given by the inverse Laplace transform of this expression, and here it is. We can see these exponential functions with the poles appearing over here, minus 1 and minus 4. Next, let us modify the transfer function by including a 0 close to the pole. Here's the modified transfer function. The 0 of the transfer function is the 0 of the expression in the numerator. And over here, I placed 0 at s is equal to minus 0.9. And this 0 is very close to the pole located at s is equal to minus 1. Let's see what will happen. By computing the partial fraction expansion of our transfer function, we obtain this expression, where now the constants C1 and C2 are given by these two numbers. We can immediately see that the 0 at s is equal to minus 0.9, that is very close to the pole s is equal to minus 1, significantly diminishes the value of the coefficient C1. Let us analyze this effect further. When we compute the partial fraction expansion, we take this transfer function, we multiply the transfer function by this expression, and we evaluate the result at s is equal to minus 1. Now, we will obtain a very small number due to this term over here. Since this part will cancel, that is, s plus 1 will not exist anymore, and by substituting here a number very close to 0.9, we will actually obtain a very small number, and that's the effect. That's why you see over here a very small number. That is, a 0 close to a pole decreases the effect of that pole on the response of the system. The impulse response is given by the inverse Laplace transform of this transfer function, and it's given over here. Let's compare the impulse responses of two transfer functions. Over here is a simple MATLAB script that I wrote. I define a complex variable s by using tf function. I define the first transfer function. I compute the impulse response of the first transfer function. Then I define the second transfer function, and I compute the impulse response of the second transfer function. And the result is shown over here. To remind you, this is the first transfer function and this is the second transfer function. The red line represents the impulse response of the system W1, and this system doesn't contain zeros. The black line is the impulse response of the system with the zero close to the pole. Here it is. We can observe that the impulse response of the system W2 initially has a large value. This is mainly due to the derivative action interpretation of additional zero, and this will be explained later on in this video tutorial. Here's the next observation. Zeros tend to increase the overshoot of the system. Namely, under certain circumstances, the zeros tend to increase the overshoot of the system step response. Let us explain this important phenomenon by considering a prototype second-order system given by this equation. Over here, zeta is the damping ratio and omega n is the natural undamped frequency. We explained the main motivation for introducing this prototype system in our previous tutorial, which can be found over here. You can click on this link and you can go over this video tutorial, and this tutorial will explain you why do we use prototype systems in systems and control. A link to this tutorial is given in the description below this video tutorial. Let's go back to our original tutorial. The poles of this system are given by this equation. These poles are illustrated in this figure. They're over here. Here's the first pole and here's the second pole. Our original prototype system can be written like this. We can simply take this omega n squared and divide the expression in the denominator by omega n squared, and here's the result. Next, let us add a zero term to our prototype system. Here's the term that we will add in the numerator. The zero is given by this expression. Over here, k is a parameter that we can vary, and we will vary this parameter in order to illustrate the effect of zeros on the transient system response. After multiplying this transfer function by this expression, we obtain the final transfer function, and here it is. Let us observe something in this transfer function. The real parts of our poles are located at minus zeta times omega n. And for k is equal to 1, the zero of this transfer function will precisely be at the location of the real part of the poles. Next, let us simulate the step response of this system for different values of k. The results are shown in this graph. Next to this graph, we will sketch another graph that will help us to understand the effect of this parameter k on the system response. First, we need to sketch the real and imaginary axis. Here's the imaginary axis, and here's the real axis. The poles of the closed loop system are located over here and over here. For us, the most important distance is this distance. And this distance is equal to minus zeta times omega n. Minus zeta times omega n is the value of the real part of our system poles. Next, let's introduce a zero to our system. The zero is given by the expression S is equal to minus k times zeta times omega n, where we can vary the parameter k. For example, let us assume that k is larger than 1 for the time being and that the zero is located over here. Consequently, this distance is minus k zeta omega n. The blue line represents the response of the system that doesn't have a zero. We can observe a very nice response. The overshoot is not significant. This case is obtained for very large values of k. Namely, for very large values of k, this zero will go to minus infinity. Now, let's see what happens when we decrease k. As we decrease k, the zero will start to approach to our imaginary axis. And let's see the effect. Over here, this magenta line is the step response of the system for k is equal to 5. For example, for k is equal to 5, 0 can be located over here. What's the effect? We can see that the overshoot is increased. Very important observation. And the rise time is decreased. Now, if we further decrease k, we will obtain this response represented by the black line. We can see that the overshoot dramatically increased and the rise time is decreased. Let's see what happens further. For k1, the 0 is precisely located over here. And the effect can be seen over here. The overshoot is increased and the rise time decreased. Next, let's push, or better to say, let's decrease this parameter further. For k is equal to 0.5, we obtain a huge overshoot. Here it is. And for k is equal to 0.35, that is for 0, for example, over here, very close to the imaginary axis, that is very close to 0, we obtain this huge response, and the rise time is decreased. Here's the MATLAB script I used to generate the graphs. First, I define the system parameters. I define zeta and I define omega n. Next, I define the complex variable s. Then, I define the first case. The first case is defined for k is equal to 0.35. Here's the first transfer function. I compute the step response and I plot the step response. Here's the second case, here's the third case, the fourth case, and the fifth case. And finally, here's our transfer function and its step response when the transfer function doesn't have a 0. Perfect. Next, we provide the mathematical explanation for the increase of the overshoot. First of all, let's make this substitution. We will define a new complex variable v that will be equal to s divided by omega n. And let's substitute this value in our transfer function given over here. As the result, we obtain a transformed transfer function given by the equation 17, where v now is a new complex Laplace variable. We can expand this transfer function like this, the first part and the second part. Next, let's define these two transfer functions, wf1 and wf2. By substituting these two transfer functions in this expression, we obtain the expression for wf. wf looks like this, and over here it should be observed that wf2 is v times wf1. Our task is to first compute the impulse response of wf. The impulse response is the inverse Laplace transform of wf, and by using this expression, we can obtain this expression. Over here, this symbol is the inverse Laplace transform operator, and tau is the scale time induced by transformation 16. Now, here I need to mention the following. In the time domain, this substitution corresponds to simple scaling of time. So tau will be related to original t, and we will have tau is equal to some constant, let's denote it by c time times t, where this ct depends on this constant omega n. Next, let's introduce this notation. yi1 is the inverse Laplace transform of wf1, and yi2 is the inverse Laplace transform of this expression over here. Since the inverse Laplace transform is a linear operator, this constant can go outside. By using this new notation, we can write our impulse response like this: yi1 of tau plus yi2 of tau. Next, it's a very well-known fact that the Laplace transform of the first derivative of a function is actually s times the Laplace transform of that function in the complex domain. Of course, if we ignore the initial conditions. For example, if f of t is a time domain function, and if f of s is its Laplace transform, then we have the following. Laplace transform of the first derivative of f in the complex domain is s times f of s, and f of s is the Laplace transform of f of t. In our case, we have a scaled complex variable v. Then, from the equation 21, that is, from this equation, we can obtain a very important expression. The inverse Laplace transform of wf2 is the inverse Laplace transform of v times wf1, and that's precisely yi1 of tau dot. We have here yi1 tau because the inverse Laplace transform over here of wf1 is defined like this, and consequently we use this rule to obtain this expression. This is a very important conclusion. This equation enables us to write the second term in the equation 24 like this. From this analysis, we conclude that the zeros introduce a derivative action during the initial part of the transient response. So what do we have over here? Again, this is the inverse Laplace transform of the transfer function given over here. That is the transfer function that doesn't have a zero. Okay, and this part over here is the transfer function that comes from the effect of the zero. We conclude that the zeros introduce this derivative. That is, since this is rapidly changing, this term will be huge initially, since the first derivative of a rapidly changing function is very large. The previous analysis can also be applied to the step response of the system simply because the step response in the complex domain is given by this equation. What do we do over here? We take our transfer function, we multiply the transfer function by the input to obtain the output. When we compute the step response, the input signal is 1 over v. And consequently, by substituting the expression for wf in this equation, we obtain this equation. And further, by expanding this equation, we obtain this equation. Now, we can simply take this part times 1 over v, and we can call this part as wf1 nu. And over here, we can also observe wf1 nu. And finally, the expression can be written like this. Again, the same conclusion happens. If we compute the inverse Laplace transform of this expression, we will compute the step response. The step response consists of two parts. This part comes from the part of the transfer function that doesn't contain zero. And the second part comes from the part of the transfer function that contains zero. This v over here is the effect of the zero. And we know that this v in the final expression for the step response in the time domain will introduce this derivative over here. And if the step response is rapidly changing, this term will be huge, and this term introduces a huge overshoot. Now, note what's happening over here. Here's our k. Here's the effect of k. If k is large, that is, if 0 is further away from the imaginary axis, this effect, that is, this derivative action will be small. However, if k is very close to the imaginary axis, this term will blow up, and our step response will blow up, and potentially the step response might become unstable. This graph is very important since it shows the step response of the transfer function wf. It also shows the step responses of its components. The red line is the step response of the transfer function wf1. To remind you, this part is a part of the transfer function that doesn't contain a zero. And we can see a relatively smooth response. On the other hand, the black line is the step response of this transfer function. This transfer function contains a zero at 0. and we can see this huge overshoot over here. This overshoot is actually due to the derivative action. And if we add these two graphs, we obtain the final step response of the transfer function WF. And we can observe the following. Our original transfer function without zero is this. The black line can be interpreted as the scaled first derivative of the red line. If we add the red line to its scaled first derivative, we will obtain the blue line, and we will see this huge overshoot. Here's the MATLAB script I used to generate the previous graph. First, I define the system parameters, zeta, omega n, and k. Over here, I define the complex variable s. Here is the first part of the transfer function, here's the second part of the transfer function, and here's the final transfer function. And I simply compute the step responses and I plot them on the same graph. That's it. Next, we will consider the case when we have a non-minimum phase zero in our system. The zeros in the right half of the complex plane are called non-minimum phase zeros. Systems with non-minimum phase zeros are called non-minimum phase systems, and control design for such systems is more challenging compared to the systems without non-minimum phase zeros. Let's consider the modified transfer function. This is our original transfer function with one small but very big difference. Over here we have a minus sign, and consequently 0 is positive, that is, the 0 is located at this position. By using our substitution, that is, by using the equation 16, here's the equation 16, and by substituting this equation in the equation 30, we obtain this expression. Now, we can use the previously defined transfer functions WF1 and WF2, and we can simply substitute them over here. And as the result, we obtain this equation. Now, you can compare this equation, equation 33, with the equation given over here, this equation. Or you can even compare it with this equation. You will see that fundamentally the only difference is in the minus sign. And here it is. And this minus sign is the direct consequence of the fact that the 0 of this system is in the right half of the complex plane. So this minus sign will create this minus sign, and this minus sign will create big problems. This term is actually a derivative action, and this term can be interpreted as the first derivative of this term. Now, if this term increases, the derivative will increase and will be positive. However, we have a minus sign, so this whole term in the time domain will decrease. And this means that the step response of the system will initially go in the negative direction, since this negative term originating from the derivative dominates the beginning of the transient response. And here's the response. The blue line is the system step response. The red line is the response of the part of the transfer function without 0. And the black line is the step response of the part of the transfer function that contains 0. And due to this negative term, we will have this very big undershoot, that is, the overshoot in negative direction. And once we add the red line and the black line, we will obtain the blue line, and we can see this undershoot. And this undershoot can create devastating effects in real life. Okay, that will be all for today. I hope that you like this video. If you like the videos I create, please press the like and subscribe buttons. Thanks a lot and have a nice day.